Hey everyone, and welcome. Today we're diving into the fundamental recipe that literally shapes how we see the world. It's the secret sauce behind everything from the glasses on your face to the massive telescopes peering into deep space. It's called the lens maker's formula. So let's just jump right in with the big question. Imagine you've got a simple, raw block of glass. How in the world do you know exactly how to grind and polish it to make a perfect lens? Is it just a bunch of trial and error? A lucky guess? Or is there a more precise way? This is the core challenge for anyone who's ever tried to build something with a lens. I'm talking about everything from a simple magnifying glass to a super complex camera system. You have to be able to tell that piece of glass exactly how to bend light to get the job done. Well, the great news is it's not guesswork at all. It's pure precision engineering, and it's all guided by one single, really elegant equation that connects the physical shape of a lens to its optical power. And that brings us to the hero of our story today, the recipe itself, the one and only lens maker's formula. Okay, there it is. Now, I know at first glance it might look a little intimidating with all the letters and fractions, but trust me, every single part of this equation tells us something absolutely crucial about how to build our lens. This is the blueprint. And as Seban puts it so well, this formula is really just a bridge. It's what connects the physical stuff, the type of glass and the shape you give it, to the optical result you actually want, the focal length. So to use this bridge, we need to understand what each part of it really means. All right, let's dive in and decode this thing. We're going to break down what each of those variables in our recipe actually stands for. First up, we have F, which is the focal length. This is our target. It's the result we're trying to get. It basically tells us how powerful the lens is. A really short focal length means you have a super powerful lens that bends light like crazy, and a long focal length means it's a much weaker lens. Next is N, the refractive index. The easiest way to think about this is that it's the quality of our main ingredient, the glass itself. Different kinds of glass have different N values, which means they have a different natural ability to bend light. A higher N means more bending power. Simple as that. And finally, we get to R1 and R2. These are the shaping instructions. This is how we physically grind the glass. Imagine that each curved surface of your lens is just a tiny slice from a much, much bigger sphere. R1 and R2 are just the radii, the size of those imaginary spheres. A small r means a very sharp curve, and a big R means the surface is much flatter. So, how does the math actually work its magic? Well, here's a really cool way to think about it. You can imagine any lens is just two separate surfaces, sort of glued together. The formula first calculates how much light bends when it hits that first surface, R1. Then, it calculates the additional bending that happens when the light leaves through the second surface, R2. And then, it just combines those two effects to give us the lens's total focusing power, F. But, like any good recipe, you can't just throw the ingredients in a bowl and hope for the best. There's some important rules you have to follow to make sure it all comes out right. So, this formula is super powerful, but it works because it relies on a few smart simplifications. First, it assumes we're working with a thin lens, where the thickness doesn't really matter. It also works best for light rays that are hitting near the center of the lens. And finally, it assumes the stuff on both sides of the lens, usually air, is the same. And you know what? For most things we build, these assumptions work perfectly. Okay, now this part is absolutely critical. To get the right answer from the formula, you have to get your plus and minus signs right. It's a system. We assume light always travels from left to right. A convex surface, one that bulges out towards the light, gets a positive R value. A concave surface, one that curves inwards away from the light, gets a negative 1. Getting these signs right is, it's everything. All right. So we've got the ingredients, we've got the rules of the kitchen. Let's see how this all comes together. How do these numbers and signs actually create the different kinds of lenses that shape our world? And here is where it all just clicks into place. It's brilliant. When you plug in the numbers for a convex lens, one that's thicker in the middle, the math automatically spits out a positive focal length. And that means it brings light together, it converges it. But for a concave lens, one that's thinner in the middle, you get a negative focal length. That means it spreads light out, it diverges it. The signs tell the story. So why does this all matter so much? Because this one little equation is the foundation for pretty much all of modern optics. Every single pair of eyeglasses made to correct someone's vision, every camera lens, every microscope, and Even the giant complex optics in the Hubble Space Telescope, they all start right here, with the principles in this formula. So, what's the big takeaway here? The lens maker's formula isn't just some abstract math, it's a design language. It's literally how we talk to glass and tell it precisely how to bend light. And by doing that, we tell it how to shape our very vision of the entire universe. And that kind of leaves us with a final thought to chew on. We've just seen how one beautifully simple equation is the hidden engine behind so much of our technology and how we see. So, what other simple formulas can you think of that quietly run the world around us in such a huge way? If you found this explanation interesting, maybe share it with a friend who'd also geek out on this stuff. And, of course, be sure to share and subscribe to the channel for more deep dives into the big ideas that shape our world. Thanks for hanging out with me.